Greetings. So the question now is, how did Archimedes get to his numbers? And that's what this part of the presentation will be about. Now, all of you have had 305, so you've learned about dummy variables. This diagram in front of us is actually going to be the equivalent of having a bunch of dummy variables in it, because I'm going to use this same diagram several times and to help us see what we're doing. Now, if you'll remember, we're going to start with triangle OA to B, and that's going to be a 30, 60, 90 triangle. So what we're going to do is I'm going to put that information in. So over here in a spreadsheet, I'm going to begin by having a measurement that we're going to call AO. We're also going to have a measurement called B to O, and we're going to have a measurement called A to B. And just so that we make sure we know exactly what we're talking about, A to O is going to be our square root of 3. O to B, or B to O, is going to be 2. So this is going to be the square root of 3. So in spreadsheet language, I say square root of 3. Now, B to O, which was along our hypotenuse, we said was 2, and A to B is 1. Now, I want to stop right here and look at these numbers for a moment. Archimedes had no problem writing down 2 and 1. We know the Greeks could manage this. But the square root of 3, he had no idea about decimals. He had to somehow say that the square root of 3 is some fraction, or that the square root of 3 is less than or greater than a particular fraction. And if you want, you can come by my office. I have a copy of the works of Archimedes where you can look at the ratios that he uses. And that was the brilliance of Archimedes. He had these beautiful ratios. The problem is he never wrote down where he got them from. And to this day, no one really knows how he got so close and how he got such good estimates of what is the square root of 3 and beyond that. But for us, we're going to use a spreadsheet, which means I'm going to get to use decimals. So I have 1.732051. Now, let's take a look at our diagram and talk about what we're going to do. If you remember in the presentation, we said, all right, we've got the big triangle. We now know that we have certain ratios that are going to hold up. And we said the ratio of AO to BO is going to give us a certain amount. So I'm going to try to write this down by typing it. So forgive me if things get a little raggedy Andy, but you will see I actually need, there's what I'm after. All right, so we're going to have AO is to BO, and we said that was going to be the same as the ratio of A to C over the ratio of B to C. Now then, what we did was we said after that, I don't know why this extraneous line is in here. Forgive me, but I have no idea why there's a line underneath my equal sign that I'm getting right there. I apologize for that. We're simply just going to have to put an equals in. All right, so now then, oh, I know what it is. Take the underline off. Ha ha ha. I'm going to leave this in the video. There you go. Now then, we're going to add 1 to both sides of this. And what I mean by adding 1 to both sides is we're going to add BO over BO to the left and BC over BC to the right. And by doing that, I'm going to get a new set of ratios, and I'm going to have AO Now plus B to O is going to be over B to O. Basically, I'm just adding a fraction to a fraction in this case. And over here on the right-hand side, I am going to now have A to C plus B to C over B to C. And because of that, and once I spread this out, get it on one line, we can now talk about what we know and what we don't know. And because of this, we know the measurement of A to O and O to B. So this is all known. And we said, oh, notice A to C and B to C is the same as A to B, which means we can solve for BC. So BC is going to actually be a number we can identify. And what I'm going to do now is, so that we can see exactly how I arrive at this, I'm going to give you the formula for BC. So BC is equal to, and I'm going to see if we can solve this. So I'm going to multiply BC up. So this sum would take its place down here, and BO would have to come up. So I'm going to have BO, whoops, BO, sorry, typing's being a problem, times, and then I'm going to have the sum of A to C plus B to C. And that is going to be over A to O plus B to O. And I'm going to spread this out so that we can see this all on one line. And so this is a calculation I'm going to want to be able to perform. All right, so on my spreadsheet over here, the next thing we're going to see is I'm going to have BO, because it's something I can now calculate. And so I'm going to put a calculation in right here, and it's going to be this calculation. So if you need to, pause the video to write those numbers down so that you know exactly what you need to see, so that we can say to ourselves, hey, this is the right calculation. And so I'm going to do the same thing. BO is being multiplied to the sum of AC and BC, and that is over the sum of AO plus BO. All right. So when I come over here, I now know that, sorry, BC is what we're calculating for, this piece right here. So my spreadsheet over here needs to be, let me escape. I need to change this to BC. All right, now that looks better to me. So now we need the measurement of B to O. So this is going to be a measurement. It's going to be a division. So I'm going to go ahead and start my parentheses. And I'm going to have the measurement for BO times a sum. So I'm going to put this sum. Well, this sum is AC plus BC, which means that it's the sum of A to B. Boom. All right, excellent. So there's my numerator divided by my denominator, and my denominator is AO plus BO. And we now have a number for B to C. So let's go look at our diagram. I now have this number. If I have that number, I can now calculate A to C. So that's the next thing I'm going to put in my spreadsheet is A to C. And we know, I'm going to go look at my drawing, A to C will be AB minus BC. So over here in my over here in my spreadsheet, I'm going to have, what did we say? We're going to have A to B minus B to C gives us AC. Now then, let's go look at our diagram. All right, so I now have this piece, I have this piece, I have a right triangle. I can now determine O to C. So that's what I'm going to do now, but I'm going to call it CO. And CO is going to be the square root, because I know I'm dealing with Pythagoras' theorem. It's going to be the square root of AO squared plus, and then we're going to have AC squared. And there is my value for C, O to C. Now, what does that happen? That means I now have the smaller triangle calculated, and this is where I'm treating this as a group of dummy variables. I'm now going to treat this little triangle as if it were the big triangle in my mind. So this horizontal O out here to the perpendicular, OA, is going to stay OA. The measurement from A up to B is now going to be A to C. So over here on my spreadsheet, I'm going to have the exact same value as I have before for O to A. But going from A to B, I need to update that with A to C. So A to B is no longer going to be 1. It's going to be the value that we got for A to C. O to B, or B to O, is now going to be replaced with C to O. All right, so I'm going to come here and we're going to say, all right, that's going to be C to O. And what I have done is I've basically said, hey, I'm doing nothing more but updating my information, because I'm going to split this smaller triangle in half and do the exact same calculations again. So watch what happens. I'm going to get a new BC, I'm going to get a new AC, and I get a new CO. And I can now drag down every single one of these values, and they begin to take on the new values that they should have had. So now let's talk about what we have here. I'm going to come over here and put in a new column called sides. We were beginning with a hexagon, which is a 6-sided figure. The next iteration is 2 times that number of sides, because we split each one of them. And now we have 24 sides. So if I come down just a couple more rows, here is where Archimedes would have stopped. Now, let's go look at our diagram for a minute. So I'm going to get rid of this last row because I don't want to go further than Archimedes right at the moment. Now, the question is, what does all of this give us? Well, let's go back and build a new column in, and let's call it perimeter. Now, let's think about the perimeter from this diagram. When we began, we were looking at the distance A to B, and we said we had a hexagon which was 6-sided. And AB represents 1/2 of one side. So for perimeter, I'm going to put in A to B, which is 1, times 2 to get the full side, times the number of sides. And that gives me the perimeter of my hexagon around this circle. And I'm now going to pull this down, and we see that these perimeters keep getting shorter and shorter, but they're really starting to get kind of close together at these last two. Now, pi is defined to be the perimeter divided by the diameter. So what I'm now going to do is ask myself, all right, what is the diameter? The diameter is twice the distance from A to O. So I'm going to come over here, and we're going to say we're going to take the perimeter divided by 2 times the distance A to O. And we see that on our hexagon, we have a perimeter to diameter ratio of 3.46. And if I were to pull this down, we're hoping to get values closer to pi. And notice we're at 3.1427 at 96 sides. Now, Archimedes did this, and when he did it, he wound up with a fraction over here. And the fraction in the book that they give you is in one of the theorems, and I believe this fraction is 3 1/7 is what we get for this value because we're on the outside. We're a little too large. And so let's think about what he does now when we go to the inside. So I'm going to come over here and we're going to do a video showing how we do our calculations to go from our inside to out.